everybody. Thank you for joining this presentation. I'm Giorgia Marson from NEC Labs Europe, and I'm going to present joint work with K.Sharad, Hien Trung, and Ghassan Karame on the security of randomized defenses against adversarial samples. So the field of machine learning is making impressive progress today. On the one hand, by relying on neural networks, we can achieve a very good prediction on many different tasks, in particular in the context of computer vision. Indeed, deep neural network models show a very high accuracy in benign settings. That means, and here is the bad news, in a malicious setting where an attacker can actually tamper with the system, neural networks show very poor performance. Researchers have shown that an attacker can generate carefully crafted inputs which cause the model to make a mistake, the so-called adversarial samples. Here is an example. We have on the left an image of a panda, which is classified with relatively high confidence and correctly. And then on the right, we have an adversarial sample, which is generated starting from this image by adding carefully crafted noise. The classifier ends up making a wrong prediction for this image with a very high confidence. Adversarial samples have been introduced in the context of supervised learning, where intuitively we want to learn a classifier starting from a set of training data, that is a bunch of inputs which come associated with the correct label. Now the expectation is that the classifier trained in this way will be able to make correct predictions also on unseen data. And violating this expectation, adversarial samples manage to fool or evade the classifier. Therefore, they are also called evasion attacks. The goal of an evasion attack is to cause the classifier to assign wrong predictions to inputs. Traditionally, adversarial samples are defined as generated by a natural input by adding a very small perturbation. And this definition is motivated by computer vision, as the attacker intuitively wants the adversarial image to look like a normal image so that it preserves its class, but in fact it is classified in a different way. The existence of adversarial samples motivated a new branch in machine learning, so-called robust machine learning classification. The idea is the goal is to design a system which is actually robust to evasion attacks. This new research field motivated several defensive proposals, and in fact, we are now experiencing an arms race between defenders and attackers, as the new defenses show some robustness to attacks, but then there come new attacks that actually break the defense. So our work continues is motivated by robust machine learning classification, and it is motivated by the following observation. All the defenses are bypassed because attackers know the details of the classifier or can emulate it. So it seems to us that the most promising approach is to introduce some unpredictability to the classification process. Shortly, we aim at answering the following question. Can randomness increase the robustness of machine learning classifiers? To answer this question, we study some selected defenses that do use randomization. We consider two existing defenses, namely cropping, rescaling, and region-based classification, and we introduce a new randomization strategy that we name randomized squeezing. We evaluate these three defenses against a wide range of attacks in a strong adversarial model, and in particular, we test each of these defenses against adaptive attacks. So the first defense, cropping rescaling, was introduced by Guo et al. And as the name suggests, it introduces a transformation that randomly crops and rescales the input image. This transformation is done both at training and at testing. At training, it serves the purpose of data augmentation to make sure that the classifier learns to recognize transformed images. And at testing, it essentially falls in the category of ensembling techniques, meaning that starting from a test sample, the classifier generates randomized different versions of the test sample. It classifies all of them, and then it averages the predictions, hopefully to obtain a more accurate prediction. Cropping rescaling is based, the robustness of cropping rescaling is based on the hypothesis that by altering the spatial positioning, destroys the perturbations added by an adversary, in case of adversarial samples. However, it preserves the visual content on the image so that the classifier will be able to still make a good prediction. The second defense, region-based classification, was introduced by Cao and Gong. In contrast to the previous strategy, region-based classification leaves the training process unmodified, so it learns a standard neural network classifier. At testing, however, it also uses an ensembling technique that works as follows. So for a given test sample, it chooses a bunch of samples at random from a small neighborhood of the test sample. It classifies all of them, and then it returns the prediction that is given for the majority of these generated samples. It relies on two hypotheses. The first is that unlike genuine samples, adversarial samples are very close to the classification boundary. It also assumes that it also relies on an hypothesis that ensembling in a hypercube around the adversarial sample will give the correct prediction. The second hypothesis implicitly requires the size of the hypercube to be large enough. This is for robustness to adversarial samples, and also to be small enough to guarantee that the classifier still recognizes correctly natural images. Finally, randomized squeezing is the technique that we introduce. Is similarly to region-based classification, does not touch the training, so it simply learns a neural network classifier. But then at testing, it introduces two transformations. The first one is randomized, and it adds uniform noise to each pixel. The second transformation is deterministic. It actually denoises the transformed input, and it is based on a previously introduced defense named feature squeezing. Randomized squeezing is based on the hypothesis that adversarial samples are more fragile than natural samples to the randomized and squeezed transformation. And similarly to the previous defense, for this hypothesis to be realistic, we need to carefully calibrate the amount of randomness added. So the reason for choosing these three defenses is that they do present some similarities, but also each of them has some particular feature that makes it interesting to compare them. The similarity is that all three defenses apply a pre-processing step. That is, instead of feeding the input to the neural network, they first process it somehow in different ways. Indeed, randomized squeezing applies two defensive layers, one that is randomized and one that denoises. Cropping, rescaling, and region-based classification both use input and ensembling to generate from one test sample multiple ones and classify all of them. And finally, cropping rescaling uses data augmentation. That is, it also affects the training step. In our robustness evaluation, we consider an adversarial model which categorizes the attacker depending on its knowledge of the defense. This is a standard approach in cryptography, which has been considered in machine learning security as well. We have the following three broad categories. In a black box attack, the adversary can only access the classifier in an input-output by submitting input and observing the output. In a white box model, this is on the opposite, we assume that the adversary has full knowledge of the system internals. In particular, it is aware of any defense in place. Finally, the gray box model encompasses all adversarial powers in between, that is, the adversary can have partial knowledge of the classifier but doesn't know it fully. Our empirical evaluation reflects this categorization. Namely, we test the three defenses on three datasets from computer vision, namely MNIST, CIFAR10, and ImageNet. And for randomized squeezing, given that is a new proposal that we introduced, we first tested against state-of-the-art attacks. Namely, we consider the strongest attacks against neural network classifiers. This results in a gray box model because the attacker knows in details the underlying deep learning classifiers, but it is not aware of the defense. Then we also evaluate all three defenses against white box attackers, which we specifically tune to bypass each defense, resulting in a fully adaptive attack. In particular, under this model, we assume that the attacker knows the transformations applied to the input, as well as the randomness distribution. So, I will now show the results of our robustness evaluation. Let's start with the gray box attacks. So here we consider randomized squeezing, and we instantiate the squeezing functions by taking all the functions proposed in the original feature squeezing paper. Namely, we apply a color bit reduction, median smoothing, and non-local smoothing. As for the randomness, we introduce uniform randomness to each pixel from the interval minus delta delta, where delta can take any value between 0 and 0.5. In particular, if we set delta to 0, we obtain a deterministic transformation because no randomness is added. And this effectively instantiates a pure feature squeezing function and allows in particular to compare our randomized proposal with its deterministic version. So in this picture, we see a first metric of comparison. We see a matrix of tiles, and each line of the matrix represents an attack. In the top part, we apply the attacks to feature squeezing, deterministic feature squeezing, and the bottom one to randomized feature squeezing. The colors of the tiles represent the success probability for the attacks. So each tile represents exactly one adversarial sample. And we see that in the case of feature squeezing, of course, given that there is no randomness introduced, we have only two possible values for this probability. Namely, a white tile means that the adversarial sample fails, while a dark blue tile means that the adversarial sample succeeded. For randomized squeezing, we see a lot of colors from a gradient, where a higher intensity color means that the adversarial sample is more likely to be successful. So now with this picture, I wanted to just give you a rough understanding of one specific property of introducing unpredictability. Namely, as we can see from the lower plot, some adversarial samples that were always successful against the deterministic feature squeezing are no longer successful, or not always, in the randomized case. On the other hand, some adversarial samples which did not succeed against feature squeezing are likely to succeed sometimes. So this is why we see almost everywhere some light color. Now this is a little bit abstract, but if we go to the concrete numbers, which we present fully in the paper, so if we look at the classification performance of feature squeezing against randomized squeezing, we actually see a similar behavior. Here I'm showing the accuracy over adversarial samples generated on TFR10 with the Carlini-Wagner attack. Again, for randomized squeezing versus feature squeezing. And the boldface numbers indicate that randomized squeezing is superior to feature squeezing. So the take-home message of this gray box evaluation is that although in some cases the added randomness seems to be very helpful, like in the first row that I'm showing here against 4-bit depth reduction, in the other cases we do not see a big improvement in robustness. This is actually not so surprising as it might seem, given that the Carlini-W attackers are not meant to bypass any of the two defenses, but only are devised to bypass a pure deep learning classifier. The results of our robustness evaluation on white box attacks are actually more interesting in that they show a more clear trend. For this evaluation, we consider two recently introduced techniques to devise white box attacks, namely the expectation over transformation, or EOT, proposed by Atali et al., and the backward path differentiable approximation, BPDA, also proposed by Atali and another set of authors. We consider these two techniques, so we consider, EOT on its own against cropping, rescaling, and region-based classification, as these two defenses only introduce randomness, and EOT is specifically devised to bypass randomized defenses. While for randomized squeezing, we devise an attack that combines EOT with BPDA, so that beyond the randomness, we can also take into account the non-differentiable component of the squeezing operator. We consider again various configurations for the parameters. In particular, in this case, we consider three values of randomness for the randomness magnitude delta, namely 0, 0.1, and 0.2 for both randomized squeezing and region-based classification, so that we can compare these two defenses. And we consider different crop sizes for crop rescaling. In the empirical evaluation, we generate adversarial samples from the ImageNet dataset, and we study the number of iterations and the distortion introduced against the prediction probability of the adversarial samples. In these two plots summarize our white box results. What we can see is that all attacks succeed in generating high confidence adversarial samples eventually. However, we also note that if the amount of randomness introduced increases, then all attackers require more iterations. This is shown in the leftmost plot. Or alternatively, the attacker requires a higher distortion to succeed. This is shown in the rightmost plot. Now, if we look more closely at the number of how the randomness impacts the number of iterations, we observe that for a fixed target prediction probability, for example, 0.6 in the picture, the defenses taken individually and for different values of randomness do require significantly more iterations to succeed. So in this case, I'm comparing the two most successful defenses, namely region-based classification and randomized squeezing, for all the values of randomness. What we can see is that if there is no randomness, only 10 iterations are sufficient to achieve the desired target prediction probability. However, if we increase the amount of randomness to 0.1 and 0.2, then the iterations required are increased by a factor of 3 to 4 in the first case and about 10 to 14 in the second case. And this shows a clear trend. That is, randomness seems to have a positive effect on robustness. So these are the main findings of our work, and they suggest some interesting research questions which might deserve further investigation. So firstly, as we can show that a specific attack device to bypass specific defenses requires more iteration as the randomness increases. And one question that is natural is, do all attacks need more iterations or more computational effort to defeat the randomness? In case this question can be answered positively, we actually have some hope in relying on randomness to provide some provable guarantees. For instance, we could achieve some meaningful robustness against computational adversaries. To summarize, in our work, we study the robustness of randomized defenses. And to this end, we propose a lightweight randomization strategy that is combined to feature squeezing. We also evaluate two existing defenses, coupling rescaling and region-based classification, along with our proposal, randomized squeezing, against various evasion attacks. In particular, we evaluate all defenses against white box attacks. And our results show that although all white box attacks succeed, they all require more effort to succeed, especially as we increase randomness. So our findings hint at two potential research directions, namely to investigate whether randomness can actually increase robustness against all, or at least all worst case attackers. And if this is the case, whether we can leverage randomness to achieve some form of computational robustness. So this concludes my talk. Thank you very much for your attention.
Orchestrating a Brighter World, NEC.